So thank you to those of you who could actually be bothered to get out of your pajamas and turn up in person. I appreciate it. And thanks to LFCS. And I'm going to thank Ohad for organising so that I'm not having to lie after. And I'm here for you. If you don't follow, please just ask. Now, this is talking with LFCS, the Laboratory for the Foundations of Computer Science. So I probably don't have to make this claim too hard, but the study of foundations is not ivory tower maths. It's world building, right? That's what foundations are. You're building worlds to solve the problem of what are the building blocks we need to solve problems using rigorous maths. That's what foundations is. And this is not an abstract question. It's a, if you like, it's a distilled question. I think it's more visible now than it was maybe when I started 20 years ago. Theorem provers are nothing more than nothing, in inverted commas, are just applied foundations. Ohad, yes.
Can you stay close to the microphone, please?
Right, so theorem provers are applied foundations. I'll take that as agreed. High-level programming languages are also, in some sense, applied foundations. Haskell, for example, wears this commitment on its sleeve, but even C is implementing in its own inimitable way a Turing machine. And so foundations, this is my slogan, are a way to study our relationship with our own understanding of what makes sense and is intuitive. If you think that functions are the most natural thing in the world, then you might prefer to live in higher order logic. If you think that sets are the thing, then you might prefer to live in ZFC, and that's fine. There's a foundation for every taste. So let's talk about naive set theory, which is my favorite mathematical foundation. You can prove loads in naive set theory, and it formalizes the idea of a set. Okay, I like that. And a set is a collection of things. It's like a bag. So naive set theory makes this precise as follows. Everything's a set. And if I have something I can say about sets, a predicate of first order logic, with sets elementhood, sorry, with epsilon. Okay, thank you. Then this comprehension here is a set. This is arguably the greatest foundation of them all, but as you may know, it's inconsistent. This is one of the great takedowns in mathematics. I'll assume you're familiar with, hands up if you're familiar with this example. Marco, if you did not put up your hand. So I'll talk you through it. This is not making you feel self-conscious or anything. This is the set of elements that are not elements of themselves. So you just unwind it like so. R is in R. If and only if R is in the set of things that are not elements of themselves. If and only if R is not an element of itself. So we have a predicate here that's true if and only if it's false, contradiction. And the first half of the 20th century was basically spent, amongst other things, trying to escape this paradox. And there were various methods, ZFC, hole-dependent types. These are all the children of naive sets and its paradox. Now, I'm going to introduce you to a set, a theory of which it is not yet known for certain that it is inconsistent or consistent. This is Quine's NF, although what I'll show you is actually something called TFT+. So complaints on a postcard, please. If anyone asks, then I'll explain what the difference is, but this will do. So levels are numbers. And everything is a set at some level. We have a set of things at level 0, at level 1, at level 2. And if phi is a stratified predicate, which means we only form B as in A when A is precisely one level up from B. then the stratified comprehension, the set of A such that phi is a set. So, okay, and then there's this typical ambiguity axiom. If phi is a closed predicate, then phi holds if and only if phi plus holds, where phi plus is a copy of phi shifted up one level. Very simple. Any questions on this before I move on? Hands up, please. Or hand? Please.
In the first bullet point here says the levels are the numbers 0, 1, 2, ... What does that actually mean, ... Because, you know, do you have like some piano axioms on integers to say what you mean by ... or what is it? What is?
So what the answer I'll give here is that I am conducting this lecture entirely in, I'll say ZF. So whatever your model of standard numbers is, I'm fine with using that. This is a consistency proof for a theory. I'm not doing any funny business in the meta theory. Does that answer your question, Kusha?
I think so. Okay, so in a sense, we are really dealing with the set of non-negative integers as understood in whatever rich set theory I want to conduct my work in.
Correct, that's right.
Okay.
Your version of NAT should work fine. Oh, to make this slightly more precise, this isn't a claim proof of consistency of NF. It's a claim proof of consistency of NF relative to, and all I need to use is in fact whole. I just need NAT and iterated power sets in the whole proof.
Okay, thank you.
Thank you for the great question. Okay, any other questions before I move on?
I'm confused by the force point. Just not familiar to me.
Oh, well, it's not familiar to most people. This is what... Oh, thank you. Sorry, mistake there. So Markov says, I haven't seen typical ambiguity before. What's that? And this is what makes NF special. It says that it's a symmetry property that closed truth is symmetric across the levels. You've not seen that before, and I'll give you a model in which it's not true in a couple of slides. So were it not for point 4, the lecture would end pretty much at the next slide. We build a model and we go home.
It says that if something holds at the lower level, then it also holds at the higher level. Correct,
and vice versa. So it's a symmetry property for the closed predicates of the universe. So if we think about NAT and power sets of NAT, this is not symmetric in this way, because at level 0 at NAT, I can say the universe is countable, and at level 1, the statement the universe is countable, which is a closed statement, is false because the universe is uncountable. So the standard iterated power set hierarchy with which you may be familiar is certainly not symmetric in this way. In fact, this whole talk is devoted to demonstrating that such a model, a claim demonstration that such a model exists. Can I carry on? Thank you, Marco. So let's just look at stratified comprehension. What does it let us do? Well, plenty of nice things. We can form the empty set, which is top left. We can form the universe. The universe of level I things is a set at level I plus 1. I think the top right set is non-empty sets. A set of AI such that there exists a BI minus 1, such that BI minus 1 is an AI. This is non-empty sets. And this is at level I plus 1. This truly is a modern tool. Tell him he's banned, he can't come back. Okay, so the point of the top right example is just notice how the levels line up, yeah? bi minus 1 epsilons ai, I minus 1 to I. And then this whole set is in I plus 1. We can build power sets. That's what this is. This is the power set. And that's fine, but stratified comprehension blocks Russell's set. Because here, we're trying to say that this just doesn't type because the levels don't match up.
The power setting is like AI prime and AI are the same level.
They are, but that's a subset inclusion. And I've defined subset inclusion there as a macro, and that's stratified. And it just says what you'd expect, that every level at I minus 1, every element at level I minus 1, if it's in AI, then it's in AI prime.
It's not predicate.
It is a predicate. I've just defined it using some syntactic sugar.
Yeah.
That's all. Thank you. Make sense? I can use syntactic sugar if I want, so long as I know I can unroll it if I need to. Note that TST plus sets are whole set flavored, not ZF set flavored. I find this quite useful. Think of level I as this purely negative type here. So if anyone's at all confused about what levels look like, just think they're like this thing, which is of course the I-fold power set of iota, the base set, right? So if you look at this and you think, well, surely I should be able to form this, just remember it makes no sense because here we're saying that AI and AI primed are at the same power set level. And here we're saying that AI is an element of AI prime. So it just does not type. It wouldn't type in simple type theory. Why should you expect it to be stratified here? That's the intuition. Put another way, this is an iterative sets hierarchy, not the kind of cumulative sets hierarchies that you might be familiar with from ZF, where you just chuck everything in. Okay. Has any questions? Ohad, yes.
It is useful to build the set. So what do I do?
Sorry, say again.
It's useful to be able to build the set, right? The set that has
these unstratified sets. Sorry, what does these?
If I want to take a set of elements, union with power sets of those elements.
Yeah, so a cumulative hierarchy. So you're very welcome to do that, just not in NF, not independent types, not in whole. So if you want a cumulative hierarchy, go to a cumulative hierarchy. This is a type theory. That's one answer. It pisses me off when people ask this because no one ever complains about simple types. I want to apply F to 2 and to lambda x2, right? But whenever people see this, they go, oh, no, I want it to be cumulative. If you just think of it like a type theory, you'll feel much better. That's one answer. The other answer is that by my understanding, and I'm not actually an expert in this, but by my understanding, NF does have a cumulative core. So you can actually build ZF-like hierarchies within NF, by my understanding. Thomas and Randall are the experts on this, okay? But from what I recall, you can do this kind of thing, but it's just a core. What NF gives you is extra power to then build more things on top of that, right? I think NF needs to work on its marketing, to be honest. I will move on. So extensionality says that sets with equal elements are equal sets. Comprehension says that you can build sets with stratified predicates. Typical ambiguity is what I like to think of as a symmetry property. It's a sum any property. If something is true at some level, and it's a closed predicate, then it's true at every level. And in a nutshell, TST is the purely negative fragment of whole. It's full plus extensional elementhood, extensional epsilon plus comprehension. And TST plus is TST with this symmetry axiom, which is what makes it all non-trivial. Now let's just build a model of TST. Oh, no, let's not. Let's just talk about why we should care. First of all, NF is minimal and canonical. It's arguably that thing that that truth that naive sets expresses. Naive sets expresses it so well that it becomes inconsistent. NF is the closest thing I know to that original idea. At some point, something becomes consistent, and we know things that are consistent like whole, and we know things that aren't consistent like naive sets. So deciding ConNF or not ConNF would locate the boundary more precisely than is currently known. NF permits a universal set, which is beautiful in and of itself. You can talk about the set of all things. Why shouldn't you be able to do that? Right? And also, there's a related theory, NFU, which is known consistent. NFU admits all elementa, which are things that are not sets, but are in the universe. So it's consistent, but you have to sacrifice the principle that everything's a set. So if it were the case that NFU is consistent and NF is not consistent, that would be God telling us, you know that intuition of set? Well, it's wrong, right? There's more. Whereas if NF is consistent, then yeah, it's okay to just be a set. I find reassuring. Yes?
The universal set here, is that stratified, so there's some level there?
Well, but top, every thank you, every variable. Second?
Repeat the question.
Right, so the question is, what is this predicate stratified? And the answer is yes, because every variable inside top has a level, and every epsilon inside top satisfies the stratification condition vacuously, because there are no variables inside top. Ohad, think whole. You've got a type of bools, bottom and top.
I have a variable there called A.
Lambda A dot top.
But it has a level.
Lambda AI dot top.
So I'm only talking about that level.
Ah, I see. Yes, so Ohad is observing that there's one universal set at every level. Sure.
Okay, thanks.
This is what you're unpacking here is what I glossed over, the difference between NF and TST plus. NF just has one universal set because it deals with stratifiability. TST plus has stratification. Thank you. Okay, any other questions? Okay, I'll carry on. Right, now we're going to build a model of TST. Very simple. It's just a power sets model. We start off from that. I want to point. I left my laser pointer in the 2000s. So V0 is NAT. We just take power sets. I mean, you've seen this. You've seen this thing before. Hands up if this is completely obvious to you, please.
You should make more than just a power set. You can do the cumulative varieties.
No, it's just a power set, literally just a power set. That's the point. This is a model of TST. So X is in VI plus 1 just when X is a subset of VI. That's all there is to it. And it's a fact that V has extensionality and it has comprehension, but it's not typically ambiguous. For example, the universe is countable at level 0 and uncountable at level 1. So it's clearly not going to be typically ambiguous. This is a model of TST, but not of TST plus. Any questions before I move on? Okay. So here I'm just defining TST plus syntax. We have the sorts. At every level, the term language is just variables of that level. We have logical connectives of fol with epsilon. We only form this when A applied to B would be well formed in whole, well typed in whole. And I'll just draw your attention to the standard De Morgan dual. Here are some examples. So this just dualizes the predicate in a standard way. Now we're going to start building some machinery for my claimed proof. If phi is closed, then let's write phi plus n, right, for a copy of phi obtained by just shifting it up by n levels. And I'm going to say that phi is necessarily true when the orbit of phi under these shifts is always true, always valid at every level in the hierarchy. So an example of something that's necessarily true is top, because no matter how you shift top, it's true. Or there exists a non-empty set. That's true at every level. Oh, here we are, I've done it here, yes. There exists, so for every B, there exists an A such that B is an A. That's necessarily true. And let's just note that comprehension, extensionality, and the family of predicates, there exist at least I distinct elements. These all hold, they're all necessarily true in our iterative sets hierarchy. So these are just facts about the universe. Any questions? Or how do we good? Okay. And here's a derivation system. So I'll give you a second to just take it in.
What are you doing now? You're building the models?
Thanks for asking. So Markov is saying, what am I doing? I'm not yet building a model. I should have said, I am defining a logic which I will use to build a model. So this will be a consistent cut-eliminating logic. Right? Once you have consistent cut-eliminating logics, there are standard techniques for building models, which we were discussing. But let's just look at this. Just in and of itself, everything down to here is just first order logic. It looks a bit odd because I've put nothing on the right-hand side. It's just the left-hand part of first order logic, but that's okay. And you see over here, with a negation, normally I'd pull this phi onto the right-hand side here, but instead I've just dualized it and left it on the left. So it's fine. And we read this as, we read one of these as saying this is inconsistent. So F bot is inconsistent. And it's inconsistent to have B as in A and not B as in A. Right? And a way to read the sequent rules is that if what's underneath is consistent, then one of the things above must be consistent. So let's try it on the top left. If F bot is consistent, then one of the things above the line must be consistent. There's nothing above the line, therefore this can't happen. This is standard first order logic stuff. And then we have these two rules. This is what's known as a deletion rule. If phi is necessarily true, then we can just delete it from the context, read bottom, top down. But I prefer to read it bottom up, that if F is consistent, then we can add to F. We can consistently add to F anything that is necessarily true.
Is there a question?
Yes.
Sam?
Yeah, I'm just confused. What's the difference between tilde phi and not phi? I mean, what are those two different symbols meaning?
So this thing here.
No, the negation rule.
Oh, here, Sam, thank you. So the question is, what's the difference between the sharp right turn and the wiggly thing? Is that right, Sam?
Yep.
So this is a predicate former negation, as familiar from first order logic. And this is the De Morgan dual of phi mentioned here.
Right, got you.
Marvelous, thank you. Thank you very much. Keep the questions coming. Any more questions? I like questions. Okay, thank you. So I'll just recap here. If we know that intuitively, if we know that phi is necessarily true, then, and we know that f is consistent, then we can consistently add phi. That's the intuition. And then this, which I've called shift, expresses typical ambiguity because truth is supposed to be symmetric. Closed truth is symmetric across levels. If we know that f phi is consistent, then, well, yeah, f phi plus has to be consistent as well. So, to answer your question another time, Markov, in a bit more detail, this is a derivation system for NF in some sense, which is just basically its FOL with 2 extra axioms. Here we are. Right, and this slide just goes through the discussion I just went through. Theorem 1. This derivation system is consistent. Now, a standard technique for proving consistency of a derivation system is to prove cut elimination and then say, aha, cut can be eliminated, therefore we cannot derive the empty sequence. That won't work, right? Because of the deletion rule. The deletion rule allows us to just add almost anything, so long as it's necessarily true. So we can't use cut elimination, but we can build a model. That's fine. And the model we build is that iterative hierarchy, which I introduced earlier. What a coincidence that we had that on a previous slide. And here's the interpretation that to prove consistency, we just have to show that every one of these rules is sound with respect to a model. And the model I choose is that if there exists a valuation that makes the shift orbit of f valid, I'll tell you what that is in a second, then there exists a valuation that makes one of the things, the shift orbit of one of the things above the line valid. The shift orbit is what we get by closing f under shifting arbitrary shifts of closed predicates. It's exactly what TA does. So I know you all get it online, but some of the people in the audience are looking a bit blank. So if you can just veuillez patienter, I will just go through this. Let's try it, right? Let's do it for this one here. Supposing that we know that the orbit of f phi is valid. There is a valuation that makes the orbit of f phi true, actually true, in the standard iterative sets model. Well, then the orbit of f phi plus is also true because the orbit of f phi is equal to the orbit of f phi plus, because phi and phi plus are in the same shift orbit. So this is now automatic. Right? No big deal. And because time is passing, I'd just like to assure you and the viewers at home that I have checked every single rule and they all work. It's all sound, I promise. And if you don't believe me, check the paper. It's written in excruciating detail. Any questions before I move on? Okay. So I claim that this system is consistent. Now, it's not just consistent, but because of box, we get extensionality, comprehension for free, because these are things that are necessarily actually true in the iterative model, right? And we get shift, we get typical ambiguity because we built it in right here on the bottom right, okay? So we have a system that is extensional, comprehensive, it has typical ambiguity, and it's consistent. Fabulous, but does that mean we are done? No. And the reason is we need to make sure that the logical connectives mean what they say they mean. So yeah, we can build a consistent set Q, but is it the case that phi or phi primed is in Q? If and only if either phi is in Q Q or phi primed is in Q. We need to control this Q to make this so. I call it witnessing disjuncts. And similarly for existentials, just because Q comes along and says there exists an A such that phi, does not necessarily mean that Q could be lying, it could be fraudulent. It could be that there is no actual A prime that instantiates it. I'm reminded of those movies where the loan shark comes to collect the money and the debtor says, I've got the money, just give me a day. And the loan shark says, no, I want it now, right? So we need to actually witness these existentials. And this is where some tricks need to be applied. Are there any final questions before I delve into how this is done? If I'm going too fast, slow me down with a question. Marcos, how's my pacing?
I don't want to slow down everyone.
Please don't be shy. Is there anything I can say to help now? Because if you're lost now, you'll be seriously lost in 2 slides' time. So.
Yes, is this what you showed us on the previous slides, your own new construction, or has this existed?
Which bit precisely?
Well, I suppose the way you design the inference rules for this.
This is new. This is novel. I did not invent these rules. These are first order logic. These rules are new. I mean, this is just typical ambiguity re-rendered. But yes, this derivation system is novel. The soundness proof is novel. And this notion of orbits.
Yeah, I guess the notion of orbits and how it helps improve consistency here, that's my question.
Perfect. Okay, happy to answer. Thank you. So why do we need to take orbits of F? It's very simple, because we want to make shift valid. Right? So we want to know that if this is denotationally valid under the line, then this will be denotationally valid above the line. And by taking orb of F, we do this quite brutally by making the orbit of what's below the line actually equal to the orbit of what's above the line. Because phi and phi primed are in the same shift orbit.
So that's orbit defined.
Yeah, that's.
Can you show me the definition of orbit?
Yeah, I think I may have actually forgotten to put it. It's there. Okay, it's up there. So orb is the least collection of predicates that contains F and is closed under typical ambiguity, under shift. It builds shift in, although note a subtlety. You can only take the orbit of closed predicates. If phi is open, then its orbit, the orbit of phi, of open phi, is just singleton phi. The orbit of closed phi is an infinite orbit of phi at every level. So we are literally building shift into the system. Yes?
So maybe I'm misremembering, but I thought typical ambiguity that we move up and down levels.
Yes, that's true.
Repeat the question.
Sorry, so thank you. The question is, well, it's not a question yet, it's an assertion. Typical ambiguity lets you move up and down. It's phi if and only if phi plus.
Right, while shift seems to only allow you to move up levels.
Well done. You're absolutely right. But remember, we can also form the. You're brilliant at your job. Thank you. So Ahad asked me to repeat the question. A question is, shift only appears to let you go up, which is true, but remember we've also got negation of phi. So if you want to go down, you assert the negation of phi. It goes up. It'll work out. But intuitively, phi can go up, but negation of phi can go up as well, which is the same thing as phi going down in some sense. Thank you. Okay. Yes.
But when we actually define orbits, we only consider the positive.
No, we go up and down.
We go up and
Yeah.
down.
Yes.
So that should be either phi plus belongs to R.
No, because it's if and only if. So if you have a phi which is equal to phi primed plus, then orbit will take you down. Yeah. Okay. Any questions from viewers at home? I will continue. Thank you. So there are two tricks I want to tell you about. The first is the shift offset cut rule. So if n is 0, we just have a fairly standard cut rule here. If we have f of phi and g of not phi, I know this is a De Morgan dual, but that's fine because De Morgan dual corresponds to having it on the other side of the sequence. If f of phi and g of not phi, then fg. And what this does is just gives you allows you to shift up. So this is the correct form of cut that we need to prove cut elimination. And if we could prove that shift offset cut is admissible, then we'd be done. Let me just try to make intuitive why we need shift offset cut. Those of you who may have done cut elimination proofs before will know that the stuff above here should not cause any problems because it's just full. And this shouldn't cause any problems because it's just a deletion. Deletion rules just don't interfere with cut elimination. So this is the only rule that could cause us difficulty. If this thing interacts poorly, that's where we'd expect trouble. And what I've done with the cut is I've literally just absorbed shifts into the cut. If we encounter a shift here on a principal formula, then we just absorb it into the cut. This goes to phi plus n plus 1. So that's where shift offset cut is coming from. Now, in retrospect, it's a natural thing to do. If we could prove this admissible, then we'd be done, because then we could say, well, sure, okay. So given a consistent f, if f is consistent, then at least one of f phi and f not phi must be consistent. So we can do a fairly standard ultrafilter completion. We can saturate. And the form of the rules is designed like if we know that this is consistent, then one of these must be consistent so we can witness disjuncts. It's a standard method. If you've seen it, you'll know what I'm talking about. But just take my word for it. If we had cut elimination for this thing, then we'd be sorted. Problem is, this cut is not admissible. Right? We cannot eliminate all shift offset cuts. However, we don't need all shift offset cuts to be eliminable. There are two cases where shift offset cut can be eliminated. One where there is no offset, so it's a standard full cut, and it just works. The other is a special case where f, g, and phi contain only closed predicates. And in that special case, Dan, yes? Okay, and I'd like to take a moment to actually show you the, here it is. So the version in ArcSieve has a typo here which I've corrected. So this is just a slightly improved version of one that's on ArcSieve, just very slightly. So let's actually do this. Supposing that everything is closed here, f, g, and for all a phi are all closed, and we want to eliminate a cut between a for all left and an exists left. I'll just mention, just by the by, this substitution here is following the form of a for all left rule, but this A primed is a bit bogus because there are no free variables anywhere. F is closed. So if I didn't think it would confuse people, I could actually just drop that substitution. But I've left it in so that I match the form of the rules. So we're going to eliminate it as follows. We're going to take this whole thing and shift it up by k steps to get this. This is a copy of gamma with everything shifted up. This is a copy of F with everything shifted up. The copy of phi with A goes to A primed with everything shifted up with K steps. And look, amazingly, we now have a standard fold cut between phi and not phi with the substitutions. And so we can eliminate it to get F shifted up and G. Now, that doesn't give us FG, but now because F is closed, we can use shift a few times to shift it down to FG. That's trick 2. It's just a brute fact. Any questions on this before I move on? Stunned silence. It's not the good silence, it's the silence of what? Okay, so feel free to ask questions. I want you to understand this. Okay, so that's trick 2. Now, let's just note, shift only acts on closed predicates. So, oh, have I missed the slide? No, okay, so I'll just fill this in a bit more. This is enough, and in the paper you'll see a 2-stage construction. I'll just tell you what it is. First, we saturate the closed predicates. We just use case 2 in the cut elimination to make decisions on all the closed predicates. Phi or not phi just gets chucked in. Now we have a theory of closed predicates, a maximal consistent set containing only closed predicates. And then we use standard fold. This has no free variables. So now we can use a standard ultrafilter completion to witness existentials, which gets us to open predicates, using part 1 of theorem 2, and thus complete this to a actual ultrafilter with witnessed existentials as required.
It's an ultrafilter.
Yes, it is.
What
is an ultra? So the question is, what's an ultra? An ultrafilter, for the purposes of this talk, is a. I'm being a bit lax, but it's a maximal consistent set that witnesses disjuncts and existentials. So building maximal consistent sets is relatively easy. The trick is to do it so that the connectives interact properly. So the classic example is, if I say to you phi or not phi, to be an ultrafilter, I have to actually also tell you whether phi or not phi, or phi or phi primed. Make sense? Yeah. Okay, good. Thank you. Great question. Any other questions? Okay. So, just some high level comments on the model, and then I will be done. The model we build, the model I claim to have built, has a 2-part structure. It has a spine of closed predicates. This is typically ambiguous. This spine is symmetric. Something that's true at level I is equally true at level I plus k. And then it has ribs. Actually, if it's a spine, it should be vertical. So I'm just turning it around. Here's our spine of closed predicates. And then it has ribs. And these ribs do not have to be symmetric. I can have phi with a free variable a that might be true at level I, false at level I plus 1. I don't care, because I don't need typical ambiguity on open predicates. That's not what the theory says. And the special cases of cut admissibility correspond to treating separately these 2 aspects of the model, the closed symmetric part and the open non-symmetric part. That's what's going on here. And in a sense, somehow you see that in the paper. Now, I've been working on ConNF for a while, some of you may know. I think what was, yes, Dan.
So these 2 methods will permit asymmetry during the construction. Are there some restrictions on the asymmetries which make them like a more of a generalized, more like a qualified generalization of symmetry rather than completely unrestricted asymmetry.
So Dan has asked how asymmetric are the asymmetries? The formal answer to your question is there is no restriction. I will show you. Let's just go through. I'll zoom out just a little so we get more on the page. You don't really need to read this. You can just look at the shape of the maths. So here we saturate the closed predicates. Saturating closed predicates is guaranteed to be symmetric because shift says so. It's impossible to asymmetrically saturate closed predicates, because if you have phi and not phi, for closed phi at different levels, then shift will bring them together and bang, everything explodes. So this is like a one-liner here. And then saturating open predicates, if you've seen one of these proofs, you'll recognize it immediately. It's a completely standard completion where we go through each predicate, and here, just look at this line here. Suppose phi or not phi is consistent, then at least one of phi or not phi and phi, or one of phi or not phi, and phi and phi primed must be consistent. And then we just, later on, you'll see me there. I just add, there, this is a line. You see, I either add phi or phi primed, and that's it. So there's no coordination. To answer a direct question, there is no coordination between the levels from line 780 onwards. Does that answer your question, Graham? Thank you. Good. Which is odd, right? It's not what one might expect. And as I was saying, indeed, I wasted, well, I didn't waste, of course. I didn't. It was all a learning experience. I spent many learning experiences trying to build models that were too symmetric. So the NFU models, these are based on Ehrenfeucht-Mostowski models, which are symmetric. And it makes sense. You see technical ambiguity, you think, great, let's build a symmetric model. And so far as I can, for me at least, trying to imitate that for NF was a dead end. I couldn't do it. I couldn't build a symmetric model of NF. This is an asymmetric model of NF, which is just symmetric where it needs to be. And that gave me some extra design freedom. Yes?
So are you saying that the previous models, there was some kind of gap in them?
They were wrong.
They were wrong.
Yes, they were wrong. So I can commend my previous efforts for many things. There's many interesting, imaginative constructs, but they're all variations on building models that are fully symmetric at every level. So I've got like a stock of symmetric models, some of which I built using nominal techniques, some of which I built using Ehrenfeucht-Mostowski techniques, but NF is quite a big loop. As I was saying this to someone yesterday, it's like you're pushing a bubble under a screen protector. And you can quite easily spend a year pushing this bubble all the way around, and then you get back where you started. And that only stopped when I admitted asymmetries. Does that answer your question?
Thanks.
At some point, I should go through my previous proof attempts and pull out all of the constructions and just say, hey, this is quite pretty. And maybe someone will find it useful. If anyone wants some symmetric universes, I've got plenty. But intuitively, permitting asymmetries is clearly a valid thing to try and do because it gives you extra design freedom. You're placing fewer restrictions on the models you can build. So this may be a proof of ConNF. I welcome review, and I welcome proposals to formalize this argument in a theorem prover. It's I would argue it's not particularly complicated. It wasn't easy to find, but in and of itself, it is cut elimination with ultrafilter completion. We have seen this kind of thing before. Okay, so Omega cheers for having a universal type. Thank you very much.
I have kind of a meta question. Maybe not. I don't want to formulate it in a way that seems impolite, but I know you like direct questions. When you have a problem that's been open for so long, it's a bit surprising when the solution is quite elementary and quite simple. And do you have like any speculate like why is it that this proof that kind of evaded us for so long or similar proofs, since it doesn't have any like really brand new mathematics or any super complicated things? Why is it that I mean, this is not a technical question, it's kind of a meta philosophical or sociological, rather, not even philosophical, sociological question. Why do you think people miss this proof?
I can't speak for anyone else. I can. So the question is, Jamie, you've made this proof seem fairly elementary. And this is Dan's version of being polite. Rather than asking, this must be wrong, because if it were right, someone smarter than you would have found it already. But the way Dan put it was, why would this simple, elementary thing have evaded us for so long? Well, I can say why it evaded me, because, as I said, I was trying to be too symmetric. I started thinking, great, I know about nominal techniques, they're all about symmetries. This is a symmetric model, therefore, it must be possible to apply nominal techniques to build a symmetric model. It just doesn't work, right? So then I thought, great, I'll try Ehrenfeucht-Mostovsky models. There must be something there. It worked for NFU. No, it doesn't. But this is slow motion, right? As I said, you can literally, I have spent a year going round in a big circle, coming back where I started. And at some point, it just dawned on me that I was imposing too much on the model. This is why I made a big deal about the spine and the ribs. It's the ribs. The spine, we know, the spine has to be symmetric, but those asymmetric ribs make all the difference. Does that?
One question.
Yes.
Is it me that you're expecting to ask the question?
Yeah, please.
Yeah, okay, good. Maybe following up on Dan's question, I'm wondering if you thought about how easy it would be to mechanize this proof. If it's, I mean, it looks relatively elementary.
I agree. I think this is highly susceptible to being mechanized with standard techniques. There's nothing, as Dan was saying, it's not exotic. It's delicate. I mean, there are tricks involved. There's some stuff that I've glossed over, but there's no monsters lurking in the proof, except possibly a mistake. But the techniques are standard.
Has it been peer reviewed yet?
No, it's been submitted to a journal, but I have not yet heard back from the referee. I'm hoping the referee's in the audience, because now you've got no excuse not to ask me questions, because I won't know, you saw my talk, so you can drop me an email. Just don't say you're the referee, we can be friends.
Okay, anyway.
Is it you, Sam?
Sorry, yeah, it's not me, no. It would be great if someone were able to mechanize it, then it might be hard to argue with.
Yeah, so I have three things. First of all, factually, you're quite right. Secondly, I'm tired, so I don't want to do this on my own. I'd need some help, please. Anybody, please. But the other thing is a moral point. I don't want to live in a world, I prefer to live in a world where people understand my proofs, rather than just, read off the lambda term. But I acknowledge, as Dan said to me over lunch, sod that, people are busy. They just want to know whether it's true or not, which is...
Right, but if you can absolutely guarantee that if someone works on mechanizing it, then they will understand it damn well by the time they've finished.
I recognize the truth of what you're saying with a heavy heart. It was hard enough actually producing this. The thought of spending another year, well, God, I hope it wouldn't come to that. So if you can fix me up with somebody, then that would be great. Does that answer your question?
I quite agree. Yeah, just advertise, find someone who wants to do it.
Yeah, absolutely. So constructively, that is a way forward. And thank goodness the proof itself, the claim proof, is not particularly elaborate. That is true. It's non-trivial, but it's not a...
It's quite self-contained. You don't rely on, you don't have to formalize the whole of mathematics to do this proof. It's quite self-contained.
Yes, you're right. I hadn't thought of it like that. That's true. Yes.
We have a question on the chat. Rickerman asks, the cut-elimination theorem allows you to do order of information without choice and countable choice. Is that correct?
That's true, actually. Dan, thank you. Thank you. Yes, thank you for coming. The cut elimination does not require choice. You do have to make choices, but the set you're making choices on naturally supports an ordering. It's just predicates. So whenever you're presented with a choice, you can just choose the smallest one. So the question was, do we use choice? And I say we do make choices, but they can be canonical. We don't need an axiom of choice. Thank you. Good question.
There's another question from Orestes.
Hi, Jamie. Hi, Jamie. Thanks for an excellent talk. So, as a dependently typed programmer,
Orestes, I'm really sorry I can't hear you. Can you speak louder, please?
Oh, yeah. Can you hear me now? Can you hear me? Okay. Right.
Go for it.
So when I saw typical ambiguity as an axiom, it really seems similar to universe polymorphism in dependently typed programming and dependent theory in general. Why is that? Because it lets you jump levels, right?
So the rest is, if I heard you, the quality isn't terribly good. I think you've said, observe that typical ambiguity looks like universe polymorphism. Is that correct?
Exactly, yeah.
Thank you so much. So as a matter of fact, there used to be a line just here that said typical ambiguity resembles universe polymorphism. And it was suggested I take it out so as not to confuse people. So thank you, Orestes. I agree. And I'll take this a step further, Orestes. Consider a dependent type theory where you actually have a type of type. So, right. And by that I don't mean that secretly it's type I of type I plus 1. I actually mean there is a universal type which is an element of itself. I dream of such a thing. So I don't recommend necessarily NF as a universe to live in and do maths unless you're into that kind of thing. But I think it would be interesting to consider, if and when this proof is accepted, consider doing the dependently typed version of this and losing the type hierarchies. Maybe we don't need hierarchies. So the counter argument to that is, well, yeah, but that's kind of cheating because the stratifiability condition is checking that you could have put a hierarchy if you'd wanted. But still, you won't have to pick a level, right? With an NS style system, you'd have a stratifiability condition, but you would still have a universal type. This would be my dream. Orestes, did that make sense?
Yeah, totally.
Perfect, thank you. Thank you for the question.
Yeah, and just a comment that if you were using universe polymorphism somehow, for example, by disallowing this term of all this universal value to exist, your orbits would be simple terms in dependent type theory. So you wouldn't need the orbit construction anymore because you could have for all L, levels L, something.
Orestes, I believe that you can hear yourself, but I can't. No, I mean, Ohad can't make it out either, so it's not just me.
Oh, okay, sorry.
Would you email me the comment offline? Maybe that would be simplest.
Sure. Yep.
Okay. So thank you, everyone. And let's thank Jamie again.
Thank you.